Hello. So today I want to talk about linear transformations, which are the functions of linear algebra, and also lots of properties of linear transformations, lots of related definitions, null spaces, matrix multiplication, determinants. These are super fundamental ideas in linear algebra. So first, let's look here at the definition of a linear transformation. So we're defining a linear transformation is a special type of function t between two vector spaces v and w. And it gets to be called a linear transformation if and only if all three of the following properties hold. We need t to respect the additive identity of these vector spaces, right? We need the zero vector of v, the input space, to go to the zero vector of w, the output space. We also need t to preserve the vector addition, right? Which is basically saying that the map T distributes. It looks a lot like a distributed law, right? That it distributes across a sum of vectors. We also need that T preserves scalar multiplication, meaning that if you have T of a scalar times a vector, you can factor out the scalar from that map T, right? So this is our definition of a linear transformation. Notice that we're really saying that it preserves the fundamental structure of a vector space, right? What is a vector space? It's a set that at least has a zero vector. It can't be empty, right? And it has two operations, vector addition and scalar multiplication. That's the key defining structure of a vector space. And then there's this long list of properties that, commutative, associative, distributive, yada, yada. But that's really the fundamental structure of the vector space is what we have listed right here. It has to preserve those fundamental structures. Zero vector, vector addition, scalar multiplication. So that's the definition here of linear transformation. And the key example, at least in the calculus sequence and differential equations, right? The derivative is probably the most famous example of a vector space, at least in that sequence of courses, right? In calc and diffie-q, right? So this is a linear transformation. And here you can say, you can easily check these three properties, right? I have, if you do the derivative of the constant function 0, you just get 0. If you take a derivative of a sum of two functions, right, that's the same as just differentiating each function separately. Right. And if you have a derivative with a constant times a function, you can factor out that constant, right? We do this all the time when we're calculating a derivative. You see, 5 times x cubed, you just sort of ignore the 5 and differentiate the x cubed. That's exactly what this is saying. Right? So here, I'm not being super formal and writing up a nice proof that it's a linear transformation or anything, but just listing out those key properties, just noticing that this maybe somewhat esoteric formalism that's living here in this definition, these are super familiar to us if you're working with, say, something like a derivative, right? Is something as common and familiar as a derivative, right? We see these properties, these three properties for a map like a derivative. Now, what I want to do is I want to then follow up with, in my title here, null space. Let's look at the definition of null space. So the null space of a linear transformation T. So we're given a linear transformation T. So we're implying here that V and W are vector spaces, right? Then sort of implied in the definition. So this is the term we're defining is null space. The null space is the set of all inputs, right, that T sends to 0, the vector 0, right, in W. So if you want to say it a little more formally, we'll write null space of T is what set? It's the set of all vectors V in big V such that T of V equals the zero vector of W. That's our definition of null space, right? So we want, I have it here once in words, once in symbols, right? That you can, the set of all inputs that go to the zero vector when t is applied. So for example, say I said find the null space of the linear transformation that we just mentioned. Find the null space of the derivative, right? Well, the null space of this map, you could say, is what? It's a set of all functions. And since we're talking about the derivative, you can, at least for our purposes here, you can assume the functions that we're talking about are mapping real numbers to real numbers. Just the standard setup in Calc 1, Calc 2, etc. So the null space of that, it's the set of all functions whose derivative equals the zero function, not just zero at some point, but zero identically as a function. So what is this saying? It's saying give me all functions such that, right, such that the first derivative is zero. Oh, okay, well this is what? This is the set of all constant functions, right? And here, I didn't do anything super fancy to find that, right? I'm just sort of thinking about how derivatives work. What kind of function would I start with to then get zero as my derivative? Well, a constant function, right? The f prime equals 0 means your slope is 0. So horizontal lines have slope 0, constant functions. Right? So this is how we could say what that null space is. And I can even write it as a span if I wanted, right? I could say this is the span of 1, right? So just pick your favorite constant function, favorite non-zero constant function. I'll take as 1, right? And then the set of all scalar multiples of that gives you all constant functions, right? So that's, so we could say, the dimension of the null space of ddx, right, equals 1, because I have just one basis vector, right? And here these ones are slightly different, be aware, right? Super subtle. This one represents the constant function 1. Whereas, be aware, new color, this one represents the number of basis vectors, right? The one is this later one, this blue one that I just highlighted. This is a dimension, right? So you're counting how many basis vectors. So that's our the very different thing that is represented by each of those ones. So, all right, so that's an example of a null space calculation. Right? Now that's all fine and dandy. There we just sort of thought about it for a derivative, right? But what if the map is a little bit more complicated, right? So let's think about, for example, say we have the function that takes we're going to take a point in 3-dimensional space, and then we're going to send it to a point in 2-dimensional space by the following method. I'm going to send xyz to the point 2x minus y plus z as the new x coordinate, and x plus y minus z as the new y coordinate. Right. So you can imagine this. Let's imagine this just in a particular example. It's a little bit hard to picture, to be honest, this map. So let's start with just some random point, just to see where one point goes here when we apply the map t. So I'm going to pick, for example, the point as my input. I'm going to pick the point 1, 2, 1. Right, so in 3D here, let's go right up to that point. So I'm going to do the point 1, 2, 1 as my input. Right, that's going to be my x, y, z. And then I'm going to take t of it. So I do t of 1, 2, 1. And then I'm going to map it to what? Well, 2 times 1 minus 2 plus 1. And then I'm going to map, this is going to be 1 plus 2 minus 1. All right, so this is going to map to what point? It's going to map to 1, 2. So that's where this blue point ends up. When we get over to the xy plane. All right, it's going to end up here at 1, 2. There we go. So there's the original point, t of 1, 2, 1. Right, it's going to get sent. It gets sent here to this point 1, 2, which I plotted wrong. Here we go. 1, 2. So there we have an example of this function mapping one point to another point. Now, 2 questions. One, is it a linear transformation? Right? Is T a linear transformation? And B, if so, find the null space. Right, so this is our little mission here. So I'm going to start with part A. So part A, it's actually kind of challenging to, it's not horrible, but it's somewhat challenging to take this function and start noodling with these 3 properties. You can do it, but it's maybe not as apparent or as clean as, or familiar, I should say, maybe as for the derivative, right? Here's a nice way to conclude this. So a nice theorem is that if a linear transformation, sorry, I should say if a function can be represented as matrix multiplication, then it's a linear transformation. So this is a really useful theorem. Because you can then take a map like this, right? You can say in our example, we had T XYZ equals these formulas, 2x minus y plus z and x plus y minus z. Right? And you can actually represent that as matrix multiplication, right? Take the vector xyz and then multiply it by the coefficient matrix 2, minus 1, 1, 2, 1, minus 1. Right. So you can represent this as matrix multiplication. And how are we doing this? Matrix multiplication takes the dot product of a row with a column. So here's row by column produces that formula, right? Because it's 2 times the x plus the -1 times the y plus 1 times z. And then similarly, you can do row by column to produce that row, right? So there we go. Row by column There we go. Row by column, 1 times x, 1 times y, and -1 times z, right? Add those quantities up, just like you do in a dot product, to produce that second row in that matrix. So that's our observation here. So I can say automatically that this T is a linear transformation. Right, so I can now analyze this in terms of null space, right? Now that I know it's a linear transformation. So, and just to briefly comment, why does this theorem work? Well, just imagine, a matrix times the zero vector is always going to be the zero vector, right? So this is far from a formal proof, right? But why is this valid? Well, because a matrix times a zero vector will always be a zero vector, right? A matrix times a sum of two vectors is able to be distributed across each, right? And if you have a matrix times a scalar times a vector, well, you can always factor that scalar out of that matrix multiplication, right? So this is why anytime you can represent it as matrix multiplication, you automatically get that it's a linear transformation. So here, then what I want to do is find this null space. Right? So let's now part B. Let's find the null space. So what I'm doing now is I want to solve what? I want to solve T of x, y, z equals 0, 0. Right? I want to know for what x, y, z does that happen? Well, what do I get? Well, I need the first equation, 2x minus y plus z. I need that to equal 0. And I need the second equation to equal 0. Right? I need both to equal 0. And here, then we can do some algebra to play around with this, right? But look at what happened here. We have two equations. With only one, with 3 unknowns, right? So we have an extra degree of freedom here. So sometimes what you do is pick one of your variables to be just some free parameter, right? So say something like z equals, let's say z equals t, right? Pick some free z. Right, so choose the z equals t. Right, where t represents some parameter. And then we can represent x and y in terms of that t. So what would I have? I'd have 2x minus y equals -t from the first equation. And I'd have x plus y equals t from the second. Right. Now, here I can then start to get these cleaned up for just a single variable, right? So let's add these equations to get, if I add these equations, I get what? I get that 3x has to equal 0 because the y's and the t's both cancel, right? So I get 3x equals 0, which tells me that x has to equal 0. And if x equals 0, then I can plug that back in to either equation to get that y equals t. So what I have now is I have a whole line, right? So what's the line that is serving as this null space? Well, it's 0, right? Because there's my x, right? It's t, because there I have my y, and t, because that was z. That was what we defined as z. Right. So there's our x, y, and z in this null space, where t is a real number. So this is, what is this? This is the line that goes through the origin, right? And it always has x equal to 0 and has y and z equal to each other, right? That's what we're getting as the null space here. So another way to look at this is t times 0, 1, 1. Another way to say that is it's the span of this vector, 0, 1, 1. So again, I got a one-dimensional null space. For this map T. Right. So I found this null space by just doing algebra, right? Just setting this equal to 0 and then solving for the x, y, and z, right? I noticed that it was an underdetermined system. So therefore I was able to pick a free variable for one of my coordinates, z, right, and solve for the others. So this is our the null space that we got, right? Let's just check this. I could actually check this by taking t and applying it to something of the form 0 tt and making sure I get 0, right? So this doesn't check that there isn't anything else. The algebra above kind of does, but it does check that at least what we found is valid. So what would this be? This would be, it's this map 2, let's see, what was it? 2 minus 1, 1, right? And then 1, 1 minus 1 was our matrix, yes. And then this with x, y, z is, well, sorry, but the x, y, z now is 0 tt, right? So what do I get here? I get 2 times 0 minus 1 times t plus 1 times t. And then I get 1 times 0 plus 1 times t minus 1 times t. And that is, in fact, the 0 vector. Perfect. Right. So it checks out that this, all vectors of that form, 0 tt, they all go to 0. So that's good. Now, I claim here it had to have a one-dimensional null space at least, because this T was mapping a three-dimensional vector space into a two-dimensional vector space, right? So something had to get collapsed. So, right? So the dimension of the null space of T had to be at least 1, because we were taking a dimension 3 space and then sort of crushing it down into a two-dimensional space, right? So lots and lots and lots of points had to get sent to the same point, right? And in particular, lots of points had to get sent to 0 because it was a linear transformation. So that's why this null space had to be kind of big, right? So that's an example where there sort of had to be a null space there. Now that's one way to see it kind of geometrically. So there's another way to see it. So here's another note again. Here's a more algebraic way to see it, more linear algebraic way to say it, I would say. So here's another way to note this. Matrix multiplication can be viewed right, it can be seen as the art of taking linear combinations of column vectors and how so? Well, this is something I think that's easiest to see just in an example. In this case, when we do T of X, Y, Z, and we represent it as this matrix multiplication, right, by this X, Y, Z. We say this is a representation of this map, right? If you want, you could write that as a linear combination of column vectors, right? So what do I mean by column vectors? Well, I mean these columns right here. Right? Think of these as column vectors, V1, V2, and V3. Right? Think of those as column vectors, and look what's right next to it. Kind of helps if you put the ones there, right? To make it a little more apparent. Look at what is right next to it there. That is just another way of saying X, the scalar X times what? Times vector V1, right? Times 2, 1. It's the scalar Y times the vector minus 1, 1. And it's the scalar Z times vector minus 1 or 1 minus 1, right? If you think about that scalar multiplication and adding up those vectors, it's exactly what's written above, right? So that's what you can think of this matrix multiplication is really just doing linear combinations, right, of these vectors V1, V2, and V3. Oop. V1, there we go. V1, V2, and V3. Right, so it's a nice way to think about linear combinations. And look at what we just showed. So the fact that the null space of T had something in it besides just the 0 vector, which this is called non-trivial. Right. There's a non-trivial null space. Was equivalent to what? It was equivalent to vectors V1, V2, V3 being what? Give you a second before I spoil a surprise. Remember what we were trying to do. When we found the null space, we were trying to find all solutions to this combination of vectors being the 0 vector, right? So think back, what property is that called if you have some way to get the 0 vector as a linear combination of vectors without, I didn't just use x equals 0, y equals 0, z equals 0. I didn't have them all 0, right? X had to be 0, but then y and z were allowed to be anything, right? I was allowed to do, say, 0 of v1 plus 3 of v2 plus 3 of v3, right? If you add that up, you get 0, 0. So what's that property? Very good. Yes, that's what I thought you said. Linearly dependent, exactly, right? Right. So that's totally equivalent to being linearly dependent. So having a non-trivial null space and the column vectors being linearly dependent, those are equivalent conditions. So linear transformation T, represented as matrix multiplication, take the column vectors of that transformation, those are linearly dependent if and only if T has a non-trivial null space, right? And conversely, it goes the other way too, right? Conversely, this is always true. So conversely, if the null space of T is trivial, opposite of non-trivial, right? If the null space of T is trivial, meaning that the null space of T is just the zero vector. Right? Or another way to say it is that the dimension of the null space of T is zero. That's another way to say it. Right. So zero dimensional null space. So it doesn't have any non-zero basis vectors, right? Just the additive identity is the only thing in the whole space. So if the null space is trivial, then the column vectors of the matrix that represents T. But if you write T as matrix multiplication, then those column vectors of that matrix, those column vectors are automatically linearly independent. So once again, the null space being trivial means that the column vectors are linearly independent. So this is now where this is going to start to relate to determinants, right? Up here, determinants didn't really show up at all because the linear transformation I was first working with, here we go, was the derivative. You can't really take a determinant of a derivative, not at least without some extra structure, right? In here, I had a matrix, right? A determinant is something we do of a matrix, determinant of a matrix. Here I had a matrix, but it wasn't square, right? It was, here I had a 2 by 3 matrix, right? So I couldn't take a determinant there either. Determinants only apply to square matrices, right? But now we finally get to where determinants relate to null spaces. So in the case where T is represented by matrix multiplication by a square matrix M, right? Then we have the following biconditionals. So we have the determinant of M is 0 if and only if the columns of M are linearly dependent right, which is if and only if T has a non-trivial null space. And because these are all biconditionals, you also get the same for the negatives of these, right? So this right, we get this nice little equivalence. We also get then the same but opposite, right? So if the determinant of that square matrix is non-zero, you get that the columns of M are linearly independent. And you get that T as a trivial null space. Right, so you get these equivalences. And where is this coming from? Well, remember that key fact about determinants. Sometimes this is called the vector independence theorem, or different names for it, right? But the one perfectly good name for it is the vector independence theorem, right? That a list of vectors are linearly dependent. If you have n vectors of dimension n, then those vectors are linearly dependent if and only if the determinant of the matrix formed by those vectors is 0, right? So this is sort of just stating that vector independence theorem again, but also using the language of null space and making it equivalent to this notion of null space. So why are we doing all of this? Maybe I'll just mention this is this bit of theory right here, especially the top connection, right? This top little chain of equivalencies is the key to finding eigenvalues, which we will soon see are phenomenally useful for lots of things. So, this is the theoretical basis for how we're going to find eigenvalues. So, before we do that, let's just look at one example here. I just want to illustrate this point of this equivalence, right? I want to see all three conditions be true or all three conditions false, depending on which one you're looking at in an example, right? So let's look at a map T that maps 3 space to 3 space, right? So now it's ambiguous. It could be a trivial null space or maybe not, right? Before we had to have a nice big positive dimension to our null space because we were mapping 3 space to 2 space. So it had to send a bunch of stuff to 0, right? Here, we're sending 3 space to 3 space. So there are lots of different ways you could do that. You could take 3 space and crush lots of it down into a single point, right? In which case there will be a non-trivial null space. Or maybe you just take all of 3 space and you just rotate it about the origin, or maybe you stretch it about the origin, or maybe some combination of those operations, right? In which case you're not crushing anything and sending it to 0 that wasn't 0 already, right? So this could really go either way, right? So let's consider this map given by, let's say we have t, x, y, z. Let's say it's given by, say I have x minus y plus 2z. Let's say I have 3x minus z, and then let's say I have y plus 5z. Right, let's say this is our map. Right. So how would I represent this map as matrix multiplication? Well, just kind of rip off the coefficients, right? So just say 1 minus 1 and 2. Those are the numbers I would need in order to take, again, think dot product, to take this and this as a dot product and end up with that, right? So that's why I'm doing 1 minus 1, 2. Then next row, 3, 0, minus 1. Once again, these are the values I would need to take a dot product of that row with that column and end up with the formula 3x minus z. And similarly, 0, 1, 5. So here I have this map, right? This linear transformation. So it is a linear transformation, right? Because I represented it as matrix multiplication. So now what I want to do is I want to look at all these equivalent conditions. So first, what I want to do is I want to calculate the determinant. So first, I'm going to, and this, by the way, this is what I was calling M, right? The matrix corresponding to the linear transformation. So first, let's calculate the determinant of M. Right, and to do that determinant, right, to do that determinant, we do it's a 3 by 3, so we can use our little diagonals trick. So we can do 1 0, 5, plus -1, -1, 0, plus 2, 3, 1, right? Where those are these three diagonals. And then I subtract the anti-diagonals, the ones with opposite slope, right? So what do I have opposite? I have 2, 0, 0. Right, it's minus 2, 0, 0. I have minus -1, 3, 5. And minus 1, minus 1, 1. Right, so that's 2, 0, 0. Minus 1, 3, 5. And 1, minus 1, 1. There. Which at this point, that original matrix is completely incomprehensible, but if you saw it created live, then it meant something along the way, right? Certain things work as animations and not as static images. This is one of them. So what happens here? I have then 0 plus 0 plus 6 minus 0 plus 15. And what is this? Plus 1, right? 21, 22. So this is 22, which on some days is known as not 0. And here, this is one of those days that's we don't really care about the 22. We just care that it's not 0. The number itself at the moment doesn't do a lot for us other than the fact that it's not 0. So here I have this determinant. So I'm going to conclude that these columns I'm going to conclude that these columns are linearly independent. What exactly does that mean? Let's unpack that definition of linear independence once again, because it's kind of a complicated definition. What it means is this. It means that if C1v1 plus C2v2 plus C3v3, if that equals the 0 vector, then what do you know about those scalars? These vectors were linearly independent. So it means the only way to end up with the 0 vector as a linear combination of those three vectors is if all of those scalars were 0, right? That's what it's telling us. So now let's look at the connection between this property and null space one more time. So in this light, suppose someone said, calculate null space of T. Well, what is the null space of T? The null space of T is the set of all vectors x, y, z such that T of x, y, z is the 0 vector. Right? But what is T of x, y, z? T of x, y, z is exactly this matrix, right? M times x, y, z. Right, so I'm just copying down that formula, at least at first. I'm just copying down that formula for our map. So I want this matrix multiplication to equal 0. Okay, now here's the sneaky bit. Reinterpret this. reinterpret this as linear combinations of those column vectors. How so? Well, it's x times 1, 3, 0. It's y times minus 1, 0, 1. And it's z times 2 minus 1, 5, equaling 0. What is this? This is a combination of those column vectors, which the determinant just told me that those vectors were linearly independent. So just like up here with C1, C2, and C3, right? If you end up with 0 using a linear combination of those three vectors, v1, v2, v3, then all of the scalars had to be 0. It's the same here. It's just C1, C2, C3 happen to be renamed as X, Y, Z. That's all, right? So what's the conclusion from this? The condition here is this, what comes after the colon, this is just a really convoluted way of saying X equals Y equals Z equals 0, right? They all have to be 0. Because why? Well, that's the definition of linear independence. Right? It says that if your scalars, sorry, if your linear combination is 0, all the scalars have to be 0. Okay, well now this set builder notation now is kind of silly. This is now a really crazy way of just writing the set containing a 0 vector. There we go, right? Because I'm saying X, Y, Z such that X and Y and Z are all 0. Well, that's just 0, right? That's just the 0 vector, set containing the 0 vector. And that's it. That's it. Look what we computed. This was the null space, right? So we just figured out that the null space of T is nothing but the 0 vector. Right? So now I have those three conditions. I observed all of them here, right? We had the determinant. So as I had a map T given by matrix multiplication by a square matrix, right? The determinant of that square matrix was non-zero. Therefore, I know the vectors are linearly independent. Now, if the vectors are linearly independent, then when I go to do a null space calculation, I say, hey, how can I get matrix times vector equals 0? Well, only if all the coefficients are 0, right? And that's the connection between all of those ideas. Yeah, so once again, here, what did we see, right? So notice in this example that we had a determinant non-zero, right? And we had that the vectors, right, the columns of M were linearly independent. And that T had trivial null space. Right. So we got to observe exactly this right here, right? This little connection. We had a non-zero determinant. The columns were linearly independent, and the function itself, the linear transformation itself, had a trivial null space. So there we go. There's a key connection between all of those ideas worked out in an example. All right. Thank you.